Hi, my name is Grace Heffernan, and today my team and I would like to welcome you to this 2021 Senior Engineering Design Day. Today, we will be presenting our project, a microfluidic system for continuous platelet separation and concentration for analytical and preparative purposes. Before we begin, I would like to introduce this awesome team: Destiny Hodges, Nick Marachanian, Natalie Sampson, Natalie Schultz, and Bethany Tolsma. Now let's dive in.
According to the CDC, about 6.2 million adults in the United States suffer from heart failure. Cardiac mechanical circulatory support devices, such as a ventricular assistant device or mechanical heart valve, are critical in the management of patients with advanced heart failure. However, as blood flows through these devices, platelets are exposed to high abnormal fluid shear stress, causing shear-mediated platelet activation, which can lead to thrombosis and ultimately heart failure. In order to prevent this cascade of events, patients are dependent on anticoagulant medications, which can prevent clotting. However, these drugs and their effects on platelet activation are only monitored in pre- and post-operative periods, with few systems available to monitor platelet activation in a point-of-care fashion. Our project is focused on the initial development of a point-of-care system for the diagnosis of thrombotic risk for a patient and their specific device. Our system is divided into 3 modules that work together to test and analyze the patient's blood. Module 1 is a centrifugation system that will automatically isolate platelets from whole blood, saving time and resources when compared to current methods. Module 2 is the design of a microchip that will continuously flow platelets through designated shear stresses, enabling physicians to mimic varying cardiovascular shear environments. And finally, Module 3 tests the level of platelet activation by mimicking the PAS, or platelet activation state assay, using a microchip and an optical system. And now I'll pass it off to Natalie Sampson and Destiny Hodges. We'll dive deeper into Module 1 with you.
The requirements for the system as a whole are listed here, as they relate to the environment, human factor, and performance of the system. Both point of care and continuous flow requirements are currently in progress and depend on the testing of Module 1. First, Module 1 is purposed with the separation of platelets from whole blood. Here you can see an outline of the module, which consists of a centrifuge, a semi-automatic PRP siphoning cap, which uses a peristaltic pump to remove PRP from the centrifuge tubes for filtering via 10 milliliter chromatography columns, ultimately resulting in GFP. The module-specific requirements relate to the accuracy of platelet separation, which is quantified first as PRP purity and then as the GFP platelet count. Unfortunately, we have been unable to test the centrifuge system with whole blood or the siphoning cap system at this time, so the platelet purity requirement has yet to be verified. With that being said, we plan on continuing with the verification testing up until design day. Initial testing of the module has shown that the centrifuge can operate as needed, reaching a speed of approximately 1,861 RPM, which corresponds to a relative force of 387 G over the required 300-second runtime. Additionally, the siphoning runtime can be adjusted by changing the motor speed of the peristaltic pump. Our testing of the 10 milliliter columns verifies the efficient separation of platelets from PRP, as all tests resulted in a platelet count greater than 20,000. I will now pass it off to Destiny to go over a demonstration of the module.
The complete assembly is still in progress, so we prepared a demonstration of the components on their own. We have the centrifuge at the bottom left, modified with a potentiometer for speed control. Then, at the top left, we have the peristaltic pump to transport the PRP from the centrifuge tubes to the column. At the center is the siphoning cap, which provides the support and alignment for the system. The motors attached to the cap will move the needles up and down to automate the process. And finally, the PRP will be dispensed at a controlled flow rate into the columns.
Module 2 is our platelet activation module, in which unactivated platelets will be passed through a microfluidic chip to test activation levels under different shear values. This is strictly a design module, and therefore we do not have results or data. The requirements for Module 2 were to design a series of microfluidic chips to emulate specific shear environments that may be found in cardiac implants. The shear values designated by the sponsor were 10, 30, 70, and 100 dynes per centimeter squared. The system would allow researchers to determine the levels of platelet activation that may be taking place in these cardiac devices so that clotting risk would be better identified from patient to patient in a point-of-care setting. Progress on this part of the project was slow going in the beginning, as there were many factors to consider in designing the chips. The fabrication process of photolithography for these chips was slow and expensive, and it was quickly made clear to us that we would not be able to complete this module by design day. So the team determined that the deliverable for this module would be creating a complete design and protocol for testing to be delivered to the sponsor for another team to continue in the future. With the help of Dr. Slepian's associates at Polytechnico, we designed a serpentine channel paired with 2 syringe pumps at either end of the channel that would pass the platelets back and forth through the chip for the time needed for full activation. For more simplicity, a single chip was designed, and the different shear rates will be achieved by varying flow rates through the chip. As stated earlier, we're not able to fabricate and test this chip. However, we will be delivering full designs and protocols for testing to our sponsors should his lab or another design day team continue this project. The assumption is that the next group to work on this module will be able to fabricate and test the chips right away based on our designs and protocols. I'll now pass it on to Destiny and Natalie Schultz to talk about Module 3.
The requirement for our third module is to be able to detect platelet activation with accuracy comparable to the PAS assay. Preliminary results suggest that this requirement is met, but we need to run additional tests to increase the sample size in order to make a final decision. Here's our fluorescence detection module. All components are commercially available and are powered by a standard wall outlet, which goes toward our goal of a point-of-care system. Our initial design used a button to power an LED light source, which would enable fluorescence of the activated platelets in the channel of the microfluidic chip that was designed for the system. However, after initial testing, we found that a higher powered light source, such as a laser diode, is required to achieve this. We measure the fluorescence using the voltage readings from a photodiode that are displayed to the user on the LCD display. We want a sample of 100% activated platelets to have a voltage reading of 5 volts in order to achieve the greatest resolution in activation detection. We expect to be able to achieve this by optimizing parameters such as the power reaching the sample and concentration of platelets.
Now for the results. This graph demonstrates that our optical system can detect different levels of light from a low concentration fluorescent dye when we replace the LEDs with a laser diode. Next, this data showed us that the optical system is detecting the level of platelet activation, but the concentration of platelets in the standard staining protocol is not high enough to yield results with the expected resolution. The microfluidic detection chip that goes with this system is designed so that the staining assay can be performed on chip. However, with fabrication delayed, the samples were tested on glass slides instead. We plan to continue optimizing our designs until the end of the semester.
Now to wrap up. To date, we have almost fully successfully completed all our expected deliverables and objectives. We successfully designed the platelet separation and activation analysis modules, and the shear emulation module was also designed successfully. We submitted the requested abstract to the ASAIO competition, and our system operating manual is slated to be completed to spec. We feel that overall, our work on this project will serve as an excellent baseline for a possible future engineering design team to continue pushing for great innovations in the field of platelet separation. Overall, we were able to learn quite a bit as a team and as individuals over the last couple semesters, between unexpected twists and turns in the development of our project and the more ubiquitous challenges faced when developing a team project solely over the internet. This experience has enriched our lives as engineers and given us fresh perspectives on issues that were previously foreign to us. Despite the many roadblocks, our team has been grateful for the challenges presented to us throughout senior design because they taught us how to be comfortable with the uncomfortable and, most importantly, how to think on our feet. Finally, we would like to recognize just a few of the amazing people that have helped us along our journey these last months. Drs. Alberto Rodali and Sylvia Bazzi were critical to some of the formative stages of our project. We would also like to thank our sponsor, Dr. Slepian, for not only creating this project, but constantly offering us advice and guidance throughout the project's development. And last but certainly not least, we would like to express our sincerest gratitude to Don McDonald, who acted as our mentor these last couple semesters. Without Don's amazing help and support, we would have been incapable of completing this project with any modicum of success. And for all he has done, we truly cannot thank him enough.
Thank you so much for watching our 2021 Senior Engineering Design Day video. We hope you enjoyed learning about our project as much as we enjoyed doing our project. We look forward to answering any and all questions that you have for us, and we hope that you have a wonderful day. Thanks.